Hello and welcome to our last presentation of today, which actually also is a premiere for us here today. Today I'm going to present you Dr. Timothy Brauner, who is a mechanical engineer and also got his PhD in mechanical engineering, focusing on combustion simulations.
Very good.
And on computational fluid dynamics. What a word. And it's a very special occasion because actually ZWSOFT acquired CHEM only last October. And it's the first time that somebody from CHEM will give a presentation about their solution and show us or talk about electronic components cooling simulations with their key solution, Phoenix. So welcome to the stage, Dr. Brauner, and thank you.
Yeah, so my name is Timothy Brauner. I'm a computational fluid dynamics engineer at the company Concentration, Heat and Momentum, or short for CHAM. I've spent the last 15 years or so working in or studying computational fluid dynamics, the last 7 of which I've been at CHAM. So the talk that I'm going to give today is about electronics cooling. I'm going to give a quick background about CHAM, Phoenix, and our relationship with ZWSOFT as well, before jumping into the electronics cooling case. The particular case that I'm going to talk about is a small electronics cooling case, because electronics cooling can take place on all sorts of scales. These you might consider a small microchip, you might consider a transformer that's the size of a building. But today we're going to look at a controller device, and I'll introduce that in more detail. The motivation for this is that we have a lot of compute taking place on edge devices these days. Something like your phone, something like the GPS on your electric scooter, and all of these things produce heat, so they need cooling. We're also seeing a lot more power density in our devices as chips shrink in size, but they still consume the same amount of power. So that gives us a challenge in removing the power from the chip. So when an electronics designer is putting together their components, we need to give them the information in order to handle the heat that's being generated in their system and how to get it out of the system. And this is where computational fluid dynamics can come in and give them more information than they have otherwise. So just a quick overview of the talk. Yeah, background. I'll then introduce the system. I'll explain what these components are that are shown here on the right. I will then discuss what we need in order to be able to do the CFD, CFD being computational fluid dynamics. I'll then present results, and I'm only going to be talking about velocity and temperature. These alone already allow us to make a fair assessment of how the device is performing. And also, I will then talk about possible remedies that these results suggest that we implement. So briefly about us being, in this case, Concentration, Heat and Momentum. We are a CFD consultancy and software house, and we have our own software package called Phoenix. CHAM was founded by Professor Brian Spalding in 1974 at Imperial College, and at that point it was the first commercial CFD company of its time. And then our main product, Phoenix, which is a general purpose computational fluid dynamics code, was introduced in 1981. And since then, we've been developing it continuously and improving it and updating its features. But we don't only develop Phoenix, we also sell it, so we can license it out to people. We use it ourselves for consultancy. And we also quite pride ourselves in our first-class user support that we offer to any user that licenses our software. And as Marcus mentioned, in October, we joined the ZWSOFT family. And so many of you might be aware that ZWSOFT has been gradually expanding into different fields and expanding its portfolio of the features and capabilities that it has. And with the acquisition of CHAM, we now bring computational fluid dynamics into the portfolio. And for me, as part of the computational fluid dynamics team, this is a very exciting time, because our team is now more than doubled in size, and we are full of momentum, and we are doing development of our software Phoenix, but we're also developing how we're going to integrate into ZWSOFT's environment. And so there's a lot going on and a lot to look forward to. I like to keep this slide in just before we go over the case, To remind everyone that electronics cooling is just one aspect of what we can do with Phoenix. There are tons of other things that can be simulated because it's a general purpose software. It's safe to say that in the 40 plus years that Phoenix has been around, it's been used to simulate just about anything that flows. So this is just a list. We'll move on to the actual case now. Okay, so this is the case that we saw earlier. It's a case that a customer had. It's not too complicated. It's just got a handful of components, but it contains a good amount of detail in the fluid dynamics that we can digest in a relatively short amount of time of this presentation. So it's a controller. It's only about 20 centimeters along the longest dimension, and it is part of a larger machinery, and it controls a subset of the machinery. So what you're looking at is in light gray, the big plane, that's a custom PCB or a printed circuit board, and on top of it sit chips. And these chips generate heat, and this heat needs to be dissipated. So the small chips each have like a low power rating, but the central chip with the heatsink on top of it, that one has a 20 watt rating, so that's quite a lot of power in that sort of form factor. So this is in an enclosure that is made of sheet metal, and then we also have, let's see, what do we? We also have some inlets on the left side, so this is an actively cooled system, it's not passive. So there's air flowing from auxiliary systems outside of the simulation into the enclosure, and the air is supposed to travel through the enclosure left to right, and then leave the enclosure on the far side where we have the slotted plate, also seen in green. So this is a conjugate heat transfer problem. That means that we're not just solving the heat in the air, we're also solving the distribution inside the solids. And the interesting, or the hard bit maybe, is to predict accurately how the temperature goes from the solid into the fluid, because this is it's a boundary layer problem. Like, what do we need from a CFD perspective in order to model something like that? So first of all, we typically deal with the geometry. We import geometry into our simulations, and then we use a background Cartesian grid. This is if you imagine maths paper or squared paper, we then put the geometry inside of it, and we cut it out of the grid. So anywhere where the geometry intersects with the grid, we have a non-brick shaped volume, and this gets a special treatment in our code. We also need boundary conditions, because all of these problems where you have partial differential equations are bounded. In this case, the boundary conditions are the inlet conditions for the velocity and the heat generation from the chips. So when you have a fluid flowing, there are two states in which it flows. It can flow laminar or turbulent. Well, these are the major states. In our case, we know that the flow is turbulent. So for our model, we also need to include a turbulence model. And for a turbulence model, we require boundary conditions that someone from the upstream department has to give us. So we need to be confident in what the information is that they're handing to us. We're of course also solving a temperature equation, and we're going to be solving that in the solid and in the temperature. We then specify the generation of heat on each of the chips, 1 watt on the small ones, 5 on the big one that was exposed, and 20 watts, which is very similar to like a CPU that you might find in your laptop for the chip that's under the heatsink. This sort of thing can get quite hot. So if it gets very hot, we might also consider including radiation models, which is something that Phoenix as a general purpose code has. But I won't be diving into that because that gets a bit carried away. All right, so let's have a look at some results. I'm going to move around the slide from the top left in a counterclockwise order, and we're going to just discuss what the flow features are that we're looking at. So the flow is entering the domain from the left through those two circle inlets that we had on the inlet plane, and it's jetting into the domain. It doesn't really spread out. This is a relatively high momentum inlet condition. So that means that we can see a red color from this color map reaching quite far into the domain. We then also see that the top jet doesn't really interact particularly much with the heatsink. It only really touches maybe the top third. So the next feature that I'll dive into in a sec is that we also have a very big dark blue region behind the heatsink. This signifies, with this legend that we have here, a close to zero velocity region. And that's not what we would like to find behind the heatsink. behind the heatsink, we would like to see velocity traveling from left to right, carrying the temperature from the heatsink out of the simulation. So this spells a problem. Furthermore, in front of the heatsink, there is a light blue region surrounded by a zero velocity region. This often implies a switch in velocity's direction. So to analyze this a little further, we're going to look at the right image. So here we're looking at the streamwise velocity component. This is the positive direction, is the x direction in which the flow is taking place. So what we see here is that upstream of the heatsink is actually a negative velocity region. So this tells us that the flow is not traveling towards the heatsink as we would like it to, but is traveling away from it in the wrong direction. So this is problematic. I mean, this is probably something we're going to have to address in the design. So the lower image is the same as the one above, but I've just chosen a different color scheme because it typically ends up helping us understand what the problem is. So here, the color white signifies a zero velocity, and the color red signifies a negative velocity. And so we can very clearly see that both upstream and downstream of the heatsink, we have negative velocities. And this is not what we want to see in this particular design. We want flow to be going in a bulk from left to right. So let's take a look at the streamline plot here. This is just to illustrate what I was trying to explain. We have the flow coming in, and then in front of the heatsink, we see some swirling motion. We have a recirculation zone. Recirculation zones are typically where things get stuck in. So we don't want heat to get stuck in this area. And behind the heatsink, we see that there's virtually no flow. So no streamlines actually make its way into there. This is also problematic because it means that there's somewhere where heat can gather up and we might end up with a hotspot, and the chips underneath the hotspot underperforming. So let's take a look at the temperature and see what that tells us about the problem. So in the top left again, but this time I've hidden the heatsink geometry. We see the temperature. The temperature reaches 94 degrees, which for electronics is still acceptable, but typically systems like to operate below 65 degrees Celsius. We also see that most of the heatsink area is that dark red. This is significant because it means that there's a buildup of heat. The heat cannot leave. In the top section where we saw that the jet was interacting with the heatsink, there is actually a gradient. We see the color go from dark blue, signifying cold, all the way up to dark red, signifying hot. So whenever we see a gradient, that means that temperature, the change is taking place. And in this case, that reflects temperature being removed. So we can also see that there's a relatively hot region behind the heatsink. So if you remember the velocity plot from just now, there was a hole or a close to zero velocity region behind the heatsink, and in there the heat is building up. So this is undesirable when designing an electronics case. The plot on the on the right, shows the surface temperature of the PCB. So we can see that the chip is getting very hot. The actual maximum temperature inside the simulation, the 94 from just now, is inside the chip. And this is something that we actually want to avoid. We can see that the other chips are doing okay. They're sort of hanging around in the 70s and the 80s, which is better at least. We also see that the 5-watt chip, the one below the CPU, is doing just fine without a heatsink because there was a jet flowing over it. The lower two images show two perspective views of the heatsink, and we can I've just kept them in here to illustrate that one half of the heatsink does seem to be working quite well, signified by blue regions, and the other half in the right image is almost all deep red, signifying no heat transfer. Let's take a look at the findings and what these findings might suggest we do to remedy the problem. So we found that the air flowing into the domain penetrates quite far into the domain rather than spreading out. We also see that the lower jet just travels through the enclosure, not really interacting much with any of the geometry. We see that the upper jet was interacting only partially with the heatsink, which is not very effective. We then also identified two regions of recirculation one upstream of the heatsink and one downstream of the heatsink. This suggests that there's very little mass of air going through the heatsink, and mass is the thing that carries the temperature. So we need to be ensuring somehow that the air and the mass that it carries goes through the heatsink. What sort of remedies might we introduce? The first one, and the least practical one, I've just left it for fun, is that we could move the CPU, but that would require a whole redesign of the PCB, so everyone will be unhappy. What we can do instead is we can move the inlet to be in line with the heatsink, so that the jet actually just flows straight towards the heatsink. We might also consider redimensioning the heatsink, because the plots of velocity showed us that the flow is deflected by the heatsink, and we established that there is very little flow going through the heatsink. So it's offering too much resistance to the flow. So if we removed, say, half the fins, or maybe we take a more engineering approach and actually do some calculations about it, we might find that we achieve, despite having lowered the surface area of the heatsink, we achieve better flow through the heatsink and thereby get reduced temperature. We could also do something which is already present in computer systems. People tend to put plastic shrouding in place. So we could introduce shrouding that goes from one of the inlets to the heatsink, thereby forcing all the air from that inlet straight through the heatsink. And lastly, maybe I'll head back to this picture. We can see that the flow behind the heatsink is also not leaving the domain particularly cleanly. It's got slotted exits, but they also have areas of solid wall between them. And some of the hot flow actually just hits the wall and then turns around because it doesn't have a place to go. And some of that recirculates in the simulation domain. So with a simple single CFD simulation, we identified a number of problems, and then we were also able to identify some potential remedies to the problem. And this is just the beginning of like a CFD study, but it's already giving us a lot of information that the designer can take and then reevaluate their design. And then we can iterate. We can implement the changes that they would like to see, and then we can run a simulation and compare how this would affect the temperatures. And then we can do all of this before manufacturing any of it, so that we only then do experimental testing at a later date and time. So I hope that I've sort of demonstrated a little bit where a simple CFD simulation can help the designer and suggest remedies. So I'd think it would be great if you could consider where CFD might fit into your workflow. And if you have any questions about where it might do come to me, and I'll have a look and talk about it with you. And I have the model on the laptop over there, so we can delve into it in detail if you would like. And with that, thank you very much.